Hello everyone, I am SV Sadhanashri and today I will be presenting experiment 4 from Parallel Computing Architecture titled Matrix Addition using Unified Memory in CUDA. This experiment was performed on Google Colab using the NVCC compiler on a system with an NVIDIA GPU. Let's look at how Unified Memory specifies GPU programming while performing matrix addition efficiently. Aim. The The aim of this experiment is to perform matrix addition using unified memory in CUDA and to analyze the performance difference between the versions with memset and without memset using the NVProof profiler. This helps us to understand both the simplicity and performance impact of the unified memory. Equipment required for this experiment, we need a PC with an NVIDIA GPU, the CUDA toolkit with an NVCC compiler, a Google Colab environment, and the NVCC for Jupyter extension, which allows CUDA code to run differently inside the notebook. Normally in CUDA programming, CPU memory and GPU memory are separate. So we have to allocate memory separately and transfer data using CUDA memcopy. With unified memory, both CPU and GPU share the same memory space. So CUDA automatically handles memory movement, making the code much simpler. For matrix addition, the operation is straightforward. C equal to A plus B. The CUDA kernel performs this in parallel using thousands of GPU threads, which makes it much faster than a CPU only implementation. The steps of the algorithms are: we initialize the CUDA device, then we set a matrix size here. It is 4096 by 4096. Next, we allocate unified memory for matrix A, B, and C using CUDA MLOP managed. We initialize A and B using with random values. We also compute the result on the CPU for verification purposes. Then we define the block and grid dimensions using 32 in 32 by 32 thread per blocks. We launch this CUDA kernel for GPU computation. Later, we compare GPU and CPU execution time, verify correctness, and finally free all allocated memories. On the host side, initial data fills matrix A and B with random numbers. Some matrix on host performs the same operation on the CPU, so we have a correct reference result. Check result compares the GPU output with the CPU output to confirm correctness. The kernel sum matrix GPU is where the GPU computation happens. Each thread calculates its own row and column using block and thread indices. It converts this into a linear index and performs mat C equal to matrix A plus matrix B. We use an if condition to ensure thread outside the matrix boundary do nothing. Since we use unified memory, there is no need for CUDA memcopy. The 2D grid and block structure lets many threads run in parallel, making the operation very fast. We tested two versions, one with memset and one without memset. The memset version initializes the output array before computation. Removing memset made the program slightly faster, about 1 microsecond improvement. Both versions produced correct results, so memset only affects performance, not accuracy. The output from CPU and GPU matched perfectly, so the computation is correct. Unified memory made the code much simpler. Before we didn't need manual memory copies. The execution time were with memset 0.032 seconds, without memset was 0.031 seconds. GPU execution was slightly faster than CPU, and removing memset gave a tiny extra speed improvement. To conclude, matrix addition using CUDA unified memory was successfully implemented. Unified memory simplifies GPU programming by removing manual memory transfers. The memset operation has almost no effect on accuracy, but a very small effect on performance. Overall, GPU execution is much faster and the results were verified to be correct. Thank you.